These observations suggest significant neutral hydrogen remained until at least 800 million years after the Big Bang. Reionization wasn't finished early. It proceeded more or less on the timescale standard models predict. If the 300 galaxies existed and were bright, why didn't they reionize the universe faster? One answer is that most of their UV radiation never escaped. Perhaps dust within the galaxies absorbed the UV photons before they could ionize surrounding hydrogen. Or maybe the galaxies were surrounded by especially dense neutral hydrogen that absorbed UV radiation in their immediate vicinity, preventing it from reaching intergalactic space. Another possibility is that these objects aren't as numerous as they seem. The surveyed area represents a tiny fraction of the sky. Maybe the researchers happened to observe an unusually dense region. If so, the actual number of such galaxies across the whole universe would be much lower, producing less UV radiation overall. The 300 galaxies add another puzzle piece, but it's not clear yet where this piece fits in the overall picture. Either they contributed to reionization in ways we don't fully understand, or they existed in a universe already more ionized than we realized. Every field of science has a foundational framework, a set of rules explaining how things work. In cosmology, that framework is called lambda CDM. It stood as our best explanation for cosmic evolution for decades. The 300 galaxies James Webb discovered might require rewriting parts of it. Lambda refers to dark energy, the mysterious force accelerating the universe's expansion. CDM stands for cold dark matter, the invisible substance providing gravitational scaffolding for structure formation. Together with ordinary matter, radiation, and the laws of general relativity, these components create a model that explains most observations of the universe. Lambda CDM makes specific predictions about how structure forms over time. In the beginning, matter was distributed almost uniformly, with tiny density variations. Over time, gravity amplified the variations. Denser regions pulled in more matter, becoming denser still. The model predicts a bottom-up growth pattern. Small structures form first. Dwarf galaxies assemble within a few hundred million years after the Big Bang. These dwarfs merge over time, building progressively larger galaxies. Giant galaxies like the Milky Way don't fully assemble until several billion years have passed. The timeline is hierarchical and relatively slow. Lambda CDM also predicts how many galaxies of each mass should exist at different times. Early in cosmic history, you should find many small galaxies and very few large ones. These predictions have been tested extensively and have successfully explained observation after observation. But the 300 early galaxies challenge this success. If even a fraction of them are genuinely massive and genuinely ancient, they exist in numbers lambda CDM doesn't predict. The model says massive galaxies should be extremely rare 500 million years after the Big Bang. Finding hundreds in a relatively small survey area suggests they're not rare at all. There are several possible resolutions. The simplest is that most of the candidates aren't actually at high redshift. If their distances were overestimated, they're not as early or as problematic as they appear. Follow-up spectroscopy might reveal that many sit at lower redshifts, where lambda CDM comfortably accommodates them. Another possibility is that lambda CDM is mostly correct, but missing some details. Maybe dark matter isn't entirely cold. Perhaps it has a warm component that speeds up structure formation in certain ways. Or maybe the initial density fluctuations from inflation were larger than we thought in rare regions, allowing faster galaxy growth there. A more significant change would involve the star formation physics. If star formation was more efficient in the early universe than current models assume, galaxies could build stellar mass faster without violating the dark matter framework. The most radical resolution is that lambda CDM needs fundamental revision. Maybe dark matter behaves differently than we think. Perhaps dark energy was stronger or weaker in the early universe. Or possibly general relativity itself needs modification to explain these observations. Most cosmologists aren't ready to abandon lambda CDM yet. The model has too many successes to discard based on one set of observations, but they're definitely concerned. If spectroscopy confirms that many of the 300 candidates are genuinely high redshift massive galaxies, lambda CDM will need significant adjustments. Joel Luhar put it directly. Finding these objects challenges current ideas about how galaxies formed in the early universe. The emphasis on challenges is polite scientific speak, for this doesn't fit what we expected at all. The next few years will determine whether lambda CDM survives intact, requires modifications, or faces a crisis demanding new physics. The 300 galaxies are forcing cosmologists to confront uncomfortable questions about their most successful theory. What if the impossible galaxies had help from the universe's earliest moments? Some cosmologists are exploring a radical idea. Maybe primordial black holes, PBHs, objects formed during the first seconds after the Big Bang, seeded the growth of these massive galaxies. Primordial black holes are different from the black holes we normally discuss. Regular black holes form when massive stars collapse. Primordial black holes formed differently. During the first fraction of a second after the Big Bang, density fluctuations in the expanding universe could have been strong enough to create black holes directly from compressed energy and matter. They could have any mass, and unlike stellar black holes, they would exist from the very beginning of cosmic time, already massive. Now imagine one of these primordial black holes sitting in a dense gas cloud during the cosmic dark ages. The black hole's gravity pulls gas inward, acting as a gravitational anchor, jump-starting galaxy formation faster than dark matter alone could. The energy released by the infalling gas could also trigger star formation in the surrounding cloud. This mechanism could explain how massive galaxies assembled so quickly. There's indirect evidence that supermassive black holes existed very early. Webb and other telescopes have found quasars, extremely bright objects powered by supermassive black holes at redshifts above 7. Growing these billion solar mass black holes from stellar seeds in the available time is extremely challenging. Primordial black holes offer a convenient alternative origin, but there are problems with this idea. We don't have direct evidence that primordial black holes exist. They are theoretically possible, but never confirmed. Also, primordial black holes should be extremely rare, if they exist at all. Having hundreds of early galaxies seeded by them requires either that PBHs are more common than we think, or that we got very lucky in where we pointed James Webb. The idea remains speculative, but it represents the kind of creative thinking astronomers are pursuing when observations don't fit standard models. Not all the mysterious early objects are blazing with star formation. Some apparently went dormant remarkably early, shutting down their stellar assembly lines while the universe was still in its infancy. Astronomers call them sleeping beauty galaxies, and they're almost as puzzling as the actively forming ones. A dormant galaxy contains stars, but isn't creating new ones. All its gas has either been consumed, expelled, or heated so much it can't collapse. In the modern universe, dormant galaxies are common, but finding them in the early universe is shocking. The first sleeping beauty was discovered in data predating James Webb's 300 candidates. Astronomers found a galaxy that existed just 608 million years after the Big Bang and showed no signs of ongoing star formation. Some of the 300 candidates Webb found might be dormant, rather than actively forming stars. Their extreme redness could indicate old stellar populations, rather than dusty young ones. Why would a galaxy stop forming stars so early? In the modern universe, we understand several quenching mechanisms. A supermassive black hole at the galaxy's center can heat surrounding gas. Mergers between galaxies can disrupt gas supplies. Ram pressure can strip a galaxy of its fuel, but these mechanisms shouldn't work effectively in the early universe. The challenge is explaining what changed to suddenly halt the star formation process. One idea involves feedback from the first generation of stars. If an intense burst of massive stars formed all at once, their combined supernovas could create a shock wave powerful enough to blow most remaining gas out of the galaxy. The Sleeping Beauties also raise questions about how common they are. If a significant fraction of early galaxies went dormant quickly, it affects our understanding of how stellar mass accumulated over cosmic history. Mass locked up in dormant galaxies represents a dead end in the evolutionary tree. The early universe appears far more diverse than our models predicted. Some galaxies formed stars at impossible rates. Others somehow formed stars briefly and stopped. The Sleeping Beauties are teaching us that early galaxies didn't follow a single evolutionary path. Among the 300 mysterious objects, 3 stand out as particularly impossible. Astronomers discovered these red monsters in a separate study, also using James Webb data. They're so massive and so early that they make the other candidates look almost reasonable by comparison. Each contains stellar populations rivaling the largest galaxies in the modern universe. Yet, they existed just 700 million years after the Big Bang. The 3 red monsters sit at redshifts around 7 to 8. That places them in the era when reionization was still ongoing. Instead, these objects contain estimated stellar masses between 80 billion and 200 billion solar masses each. For comparison, the Milky Way contains roughly 150 billion solar masses of stars. Finding one such massive galaxy at that epoch would be surprising. Finding 3 in a relatively small survey suggests they might not be as rare as theory predicts. What makes these red monsters especially problematic is their efficiency. Calculations suggest they turned 40 to 50% of available gas into stars. That's unprecedented. No galaxy in the modern universe achieves such high efficiency. These objects somehow bypassed the feedback mechanisms that normally prevent efficient star formation. If these objects formed through the standard hierarchical process, they represent the merger of dozens or hundreds of smaller proto-galaxies. But there wasn't time for that many mergers. The alternative is that they formed through a more direct collapse process. This top-down formation contradicts Lambda CDM's bottom-up predictions, but the observations seem to demand it. The 3 red monsters also raise questions about dark matter. To support such massive galaxies, they'd need to sit in extremely massive dark matter halos. Building such massive halos within 700 million years pushes the limits of what cold dark matter models allow. The red monsters pushed already strained theories to their breaking point. They're questioning fundamental assumptions about how quickly massive structures can assemble in the early universe. The story we've told about the universe's earliest galaxies is changing. For decades, textbooks painted a picture of gradual growth, with small galaxies slowly merging into larger ones over billions of years. The first chapter of cosmic history described a universe emerging slowly from darkness, cautiously building its first structures. The 300 galaxies James Webb discovered are forcing us to rip out that chapter and start over. What we thought we knew was that the first stars formed around 400 million years after the Big Bang. Over the next few hundred million years, they began clustering into small proto-galaxies. These dwarf galaxies were the building blocks. They merged pairwise, combining their stellar populations, gradually building incrementally. Hubble found small blue galaxies in the early universe exactly as predicted. Everything made sense. Then James Webb started observing. The 300 candidates appeared far too bright and massive for their age. The Sleeping Beauty galaxies showed stellar populations that formed and shut down impossibly early. The 3 red monsters contained stellar masses that shouldn't exist for billions of years. The entire carefully constructed narrative began unraveling. The new picture emerging from Webb's data is more violent and chaotic. The early universe wasn't cautious. It was aggressive. Galaxies formed faster, grew larger, and evolved quicker than anyone predicted. Star formation rates exceeded modern extremes by factors of 5 or 10. Gas collapsed efficiently despite processes that should have prevented it. This revised history has profound implications. If massive galaxies formed so early, they would have ionized the universe faster, changing the timeline of reionization. Their stars would have produced heavy elements sooner, enriching the early intergalactic medium. Supermassive black holes could have grown earlier and larger. The formation of large galaxies early in cosmic history also affects how we understand galaxy evolution overall. This isn't just about fixing numbers in theoretical models. It's about fundamentally reconceiving what happened during the universe's infancy. The first billion years were apparently more dynamic, more efficient at building structure, and more capable of producing mature galaxies than we ever imagined. The revised chapter reads very differently from the old one. Instead of slow and steady, it's fast and furious. And we're still not sure we understand the plot. Right now, the 300 candidates exist in scientific limbo. They're tantalizing, puzzling, and potentially revolutionary, but they're not confirmed. The next phase of research will determine which candidates are genuinely ancient, massive galaxies, and which are imposters. That determination requires spectroscopy, and astronomers are already planning the observations. Spectroscopy doesn't just take pictures. It dissects light into its component wavelengths, revealing absorption and emission lines from atoms and molecules in the source. By identifying the lines and measuring their shifted wavelengths, astronomers determine the exact red shift. This measurement is far more precise than photometric estimates from broadband imaging. For the 300 candidates, spectroscopy will answer the most basic question: how far away are they really? If most turn out to have lower red shifts than estimated, they're not as early or as massive as they appear. If many confirm high red shifts above 7, the crisis for cosmology intensifies. Spectroscopy also reveals what's producing the light. Active galactic nuclei show strong emission lines from hot gas near supermassive black holes. Quasars have very different spectral signatures from normal galaxies. By examining the spectrum, astronomers can definitively determine whether an object is a galaxy, quasar, or something else. Chemical composition and stellar population age estimates also improve dramatically with spectroscopy. Webb is already conducting spectroscopic follow-up on selected targets. The brightest candidates get priority since they require less observation time. The first results are starting to appear. Some candidates have been confirmed at high red shift. Others turned out to be at lower red shifts, ruling them out as impossible early galaxies. The picture is becoming clearer, but remains incomplete. Future spectroscopic surveys will observe larger samples more efficiently. Webb will continue follow-up observations for years. Ground-based telescopes like the extremely large telescope under construction in Chile will add their capabilities. Together, these facilities will eventually spectroscopically confirm or reject most of the 300 candidates. Each confirmed high redshift object becomes a laboratory for testing theories about early galaxy formation. Within 5 years, we'll have spectroscopic confirmation for most of the brightest candidates. That data will determine whether the 300 galaxies represent a genuine crisis for cosmology or a temporary anomaly, explained by more careful analysis. When observations clash with theory, scientists face a fundamental choice. Either the observations are wrong, or the theory needs revision. For the 300 early galaxies, we're fairly confident the observations are real. James Webb Space Telescope is working as designed. The photons it detected genuinely came from distant objects, which leaves the uncomfortable possibility that our theories need major changes, maybe even new physics. New physics is a phrase scientists use carefully. It typically means discovering that our current understanding is incomplete, not entirely wrong. Several areas of physics might need revision to explain the early galaxies. The most obvious is star formation theory. If star formation efficiency was dramatically higher in the early universe, existing physics might explain it without requiring new laws. That's refining existing physics. Dark matter presents another possible avenue for new physics. We know dark matter exists, but we don't know what it is. Current models assume it's entirely cold. Maybe dark matter has properties we haven't discovered. Perhaps it interacts weakly with itself in ways that accelerate structure formation. That would constitute genuinely new physics. Some theorists are exploring modifications to gravity itself. What if general relativity isn't the complete story? Maybe gravity works slightly differently on large scales, or at early times. Such modifications would represent major new physics. Another possibility involves dark energy. If dark energy evolved over cosmic time in unexpected ways, it could affect structure formation rates. Here's the critical question. How much can we adjust existing theories before we have to admit we need genuinely new physics? If tweaking a few parameters or refining models of star formation efficiency solves the problem, that's normal scientific progress. But if no amount of parameter tweaking makes existing models match observations, we face a real crisis. That's when scientists seriously consider new physics. We're not there yet with the early galaxies. Many avenues remain to be explored within existing frameworks, but we're closer to that threshold than at any time in recent decades. The history of astronomy includes several cases where new observations forced genuinely new physics. Perhaps the early galaxies will ultimately fit within lambda CDM with some adjustments. Or maybe they're pointing to gaps in our understanding that require new particles, fields, or fundamental laws. The 300 galaxies are definitely pushing. Whether they'll break our theories remains to be seen. James Webb's discovery of 300 mysterious galaxies raises an unsettling question. If we missed these objects completely until now, what else are we not seeing? Space is vast, and our observations cover only tiny fractions of the sky. The universe might be filled with impossible objects we haven't found yet, because we weren't looking in the right way. The objects were there all along, broadcasting their presence but invisible to instruments that couldn't detect their stretched redshifted light. How many other types of objects are currently invisible because we're using the wrong tools? Extremely distant quasars might be lurking beyond current detection limits. Primordial galaxies, even older than the current record holders, might be waiting for discovery. Webb can see back to potentially 150 million years after the Big Bang under ideal conditions. What if galaxies formed even earlier, at 50 or 100 million years? Dark galaxies represent another possibility. These hypothetical objects would contain large amounts of dark matter and gas, but few stars. With minimal star formation, they'd produce almost no light. Current telescopes detect galaxies by their starlight. Dark galaxies would be effectively invisible. Then there are the exotic theoretical objects that observations haven't yet confirmed or denied. Black hole stars, if they existed, might be more common than we realize. Intermediate mass black holes remain mysterious. We know stellar mass black holes exist, formed from collapsing stars. We've found supermassive black holes in galaxy centers, but intermediate mass black holes are rarely observed. The early universe might have produced them in significant numbers. Population 3 stars, the very first stars, made entirely of hydrogen and helium, have never been directly observed. Theory predicts they existed and should have been extremely massive, but maybe some survived longer than expected or formed later than we think. Finding an actual population 3 star would be revolutionary. The point isn't that all these exotic objects definitely exist. Most probably don't. The point is that the universe is vastly larger and potentially far stranger than the portion we've observed. Every time we build a more capable telescope or develop a new observational technique, we find unexpected things. The 300 impossible galaxies taught us that the early universe was more active and more capable than we imagined. What will we learn next? What other assumptions will be challenged by future discoveries? Webb will continue observing for years. Other telescopes in planning stages will add different capabilities. The flow of discoveries won't stop. Somewhere out there, probably in multiple locations, objects exist that would astonish us if we could see them. They're waiting for the right telescope, the right wavelength, the right observational strategy. Some might challenge our understanding even more radically than the 300 galaxies do. The universe has shown repeatedly that it's more creative than our imaginations, more diverse than our theories, more surprising than our expectations. The impossible galaxies are just the latest reminder that we're still learning the universe's deepest secrets. What we discover next might be even stranger. We're at the edge of a new era in cosmology, defined by the impossible galaxies James Webb has revealed. The science is moving fast, and every new piece of data could redefine our place in the cosmos. Don't miss the next revolution in astrophysics. Hit that like button, subscribe to Stellify Science, and let us know in the comments. Do you think these are genuinely impossible early galaxies or a completely new type of object? We'll see you in the next exploration.